Alright, so we're going to be starting a new chapter where we'll be looking at vectors. So we're going to look at what vectors are, some of the characteristics of vectors, some rules, some equations, and just using them to model real life situations. So first things first, this video we're going to be looking at just the basic what vectors are. So a vector is something with a magnitude and a direction. Okay, so it's got a direction and then you know how far it's going along. And you might see something like a notation when we say like A to B. Okay, so this is like a vector notation, and it just means we're going from A to B. So if I was to point A here and then B here, the vector A to B will be this vector here, A, like this. And they might give you a little letter, so they might say this is just lowercase a like this. So that vector A to B is just represented by small case a. Right, if I do the same vector now, okay, like this is C to D, and C to D is parallel to A to B, then C to D is also the same vector A, okay, because it's the same length as A to B, and it's in the same direction as A to B, so because they're parallel, so that means it's represented by the same letter A. If I draw another one, like here, but now this is D to E, but now this is twice the length of A to B, then D to E is in the same direction, but it's twice the length, twice the magnitude, so it's now represented by 2A. If I go the opposite way around, so let's say E to F like this, but now the arrow is in the opposite direction, but with the same direction and same magnitude, then this is just represented by minus A, like so. Okay, so that's basically how vectors, or the very basic notation of vectors. If I now have, let's say, A, like here, this is B, and then we have C here, and I told you that A to B is A, and B to C is B. That means I can say this is going to be small a, this is going to be small b, and I'm trying to find a to c. Okay, so trying to find this vector here, a to c. So what we can do is we can just find a root from getting from a to c. So a to c I can say is essentially going from a to b, then I add from b to c. That way I start at a and get to c. So a to b was represented by small a and b to c was small b. So this vector a to c is just a plus b like this. And this is known as the triangle law, and it's a very important law because it just means that if you want to start at one point and finish at another point, you just have to find a root which gets there, and then that would be the vector of that basically direction. All right, so that's the very basic form of vectors that we have to be aware of. So if we solve a question, let's look at this one here. We have in a triangle ABC, AB is A and AC is B. So A to B is A to B, no. So the directions are important, right? So I'm going to just draw a bit larger, like this. So A, B, C. So A to B is represented by small a, and A to C is represented by small b. P is the midpoint of AB, and Q is the midpoint of AC. So P is here, and Q is here. Right in terms of A and B, B to C. Okay, so B to C. So when we do this, we just want to try and find the root from start to end. So we're going from B, and we want to end up at C, so we have to go in a route that we do know, right? So we go B to A plus A to C. Now, if A to B was A, then B to A is just going to be the same direction, but opposite direction, right? So it's going to be negative A. This is going to be negative A plus A to C, which is just B like this. Part 2, A to P. Now, A to P, well, P is halfway along A to B, right? So I can say this is going to be half of A to B, which is equal to half of A. Part 3, A to Q, once again, is half of the way along from A to C. So this is going to be half B. And finally, P to Q, well, I can go P to A plus A to Q. That's the route I'm going to take. And P to A is the same thing as minus A to P, right? This is the opposite direction, plus A to Q. And we found A to P earlier in part 2 here. So I can say it's going to be minus a half plus A to Q, which was in part 3, minus half A, sorry, plus half B, and that's going to be our P to Q. Right, in B, show that P to Q is parallel to B to C. Okay, so the way we show something is parallel is if they have the same vector, but it's a certain factor. So for example, let's say we have the vector 2A plus 4B. This is actually parallel to the vector 4a plus 8b. The reason being is because with this vector here, I can take the 2 out and I get 2a plus 4b, right? So essentially it's the same vector, it's just this one is multiplied by a factor lambda, we'll call it, okay? So if this is the case, then we know that these two vectors are parallel. Something that's not parallel is, for example, 2a plus 4b is equal to 4a minus 8b. Because if I take the 2 out here again, factorize by 2, this vector here is not the same as this vector here, so it's not going to be parallel. So two parallel vectors are when we have a plus b is equal to some lambda a plus b as well. So if it's certain factor or certain multiple of each other, that's when we know two vectors are parallel. So going back to this question here, it says PQ is parallel to BC. So PQ, the vector PQ we found earlier was minus half a plus half b, and BC we found earlier to be minus a plus b. Okay, and so what I can do is I can take the half out of this here, right, factorize it, and you're left with minus a plus b. And what you notice is actually PQ is equal to half of BC, meaning that they are going to be parallel vectors. So that's how you'd go about showing that they're parallel. Okay, so for vectors, we can also draw it on a graph, and like here. But instead of the y and x graphs, what we do in vector form is we call it the I and j graph, or I and j notation. So for example, we can say that the vector A is equal to 2i plus 3j. Or in column vector form, it's going to be 2, 3. Okay, so the I on top of the j. What this represents is this A is going to be 2 here and 3 here. So it's going to be this point here. So this A is represented by this position on the graph. Okay. B could be maybe like minus 4i plus 3j. And same thing, so minus 4i 3j here. So this would be represented by B, like so. And with this, what we can do is we can add, subtract, multiply. So I can find maybe like a plus b. This is just simply in column vector form 2, 3 plus minus 4, 3, because they are independent. I and j's are separate. So this will be minus 2 and 6, like so. We can even do like 2a, which is going to be 2 times 2, 3. So multiply to each side, we'll get 4, 6. And this is just the sum and multiply rule is just the same as we've been learning all this time. Furthermore, we can also find the magnitude, because we know where it's going to be, but sometimes it might be useful to work out how long this line is going to be. So we call that the magnitude. And we say, for example, magnitude of A. Okay, so let's say A is xi plus yj. Then this is just finding the square root of x squared plus y squared, like so. So for example, if A was like 3i plus 4j, the magnitude of A, the length of A will be the square root of 3 squared plus 4 squared, which is 5, like this. From here, we can also find something called a unit vector. And a unit vector is denoted by the notation, this uppercase here. This is represented by hat. So you read this as a hat, essentially, and it represents a unit vector. And a unit vector is a vector with magnitude 1 of 1. So you can see in the previous example here, this had the magnitude of 5, right? So we can find a unit vector of A, which has a magnitude of 1. And the way we do that is A hat is equal to A over the magnitude of A. This is the equation to find the unit vector. So for in this example, it's going to be A hat is going to be 3i plus 4j over the magnitude, which is 5, like this. And we can prove that it's a magnitude of 1, because if I find the magnitude of A hat, it's the square root of 3 over 5 squared plus 4 over 5 squared, which is going to be equal to the square root of 25 over 25, which is just 1, so it's true, right? This is useful for later on. It's essentially at the number 1 in vector form, essentially. And finally, they might ask you to find some angles. So for angles, normally we use tan theta, which is y over x. Okay, so for example, let's say I have a vector b, which is I plus root 3j. So if I was to draw it, it'll be I is 1, root 3 is roughly here, it's going to be roughly here. And I want to maybe find this angle theta, this one here, relative to the positive x-axis. As you can see, if I draw a line here, it's going to be a right angle triangle, right? So that's where this equation comes from, because we know theta, we're trying to find theta, and we know the height is root 3, we know the base is 1. So tan theta is going to be root 3 over 1, theta is going to be 60 degrees, stuff like this, okay? And so that's all the basic important things you need to be aware of when dealing with vectors. We're going to be looking at more difficult vectors or more difficult problems that we solve using vectors in the next videos.